Hello everyone, welcome to my group theory lecture. In this lecture, we study subgroups. So what is a subgroup? A non-empty subset of H of a group is called a subgroup of G if H itself forms a group relative to the operation, uh, you know, uh, dot in G. So H, we say, the H is a subgroup if it becomes, in other words, it becomes a group with the inherited group structure from, G. So if H is a subgroup of G, we simply write this notation, right? Here, like you see, like the what is it, less than or equal to, right? But this has nothing to do with inequality. What this means is H is a subgroup of G. Clearly, G is a subgroup of itself, of course, right? And also the singleton set with the identity element, okay, that is also clearly a subgroup of G. So in that sense, G and also this singleton set with identity are called trivial subgroup, trivial subgroups of G. Okay, before we continue, let us take a look at the following lemma, right? It lists some basic properties of a group. If G is a group, then its identity element is unique. So there is only one identity, basically, right? What it says. Each element A has a unique inverse. So A inverse, right? So the inverse element of each element also exists uniquely. And for any A in G, the inverse of inverse element is A itself. And for any AB in G, A times B inverse is same as B inverse times A inverse. Okay, this can be proven. Proof, the proof of that these properties is not that hard, and it's left as exercise. In fact, they are part of a group theory problem set 2. Yes, so I made a hyperlink to this. So just click on the word group theory problem set 2, then it'll take you there. Okay, so an important question, of course, is what when you have a non-empty subset of a given group, how do we show that that H is a subgroup, right? So of course, by definition, in order to show that a non-empty subset H of a group G is a subgroup, we need to check the following thing. H has to be closed under the same, inherited operation, right? Okay, so operation in G. In other words, for any A, B in H, right, A times B has to be also in H. Oh, I missed some weird typo. Okay, sorry about that. I fixed it after uh, I finish recording this lecture. Second one is, the identity has to be also in the set, right? H, and obviously for any A in H, A inverse has to be also in H, right? Inverse element. So there is a one, earlier, right? We learned like what, for a set with operation to be a group, right? There are axioms that need to be met or okay satisfied. That is one axiom is missing, right? In the definition of a group, associative. The operation has to be associative, but it is automatically satisfied. Why? Because H is a subgroup of, I mean, subset of this G. G is already a group, right? So, you pick any three elements in G, they satisfy, you know, in other words, this operation satisfy the associative law. So we don't have to check that, okay? But in fact, there is even like a simpler uh, criterion to check if non-empty, a non-empty subset of a group is there's another type I missed, sorry, is a subgroup of a group. So that's this lemma. So a non-empty subset H of a group G. Okay, here I didn't. I should have mentioned that G is a group. G is a group, right? So a non-empty subset H of a group G as a subgroup if and only if for any AB in H, AB inverse also belongs to H. That's the only thing you have to check. So why is that true, right? Let's check that. I wrote down proof here, but let's go to my notepad. So here's a lemma. Let G with this operation, right, be a group. Then a non-empty subset H of G is a subgroup of G if and only if uh, for any A, B, two elements in H, A, B inverse as in H. Okay, so that's all you have to show. So let's prove this lemma. Okay, so as usual, I'm going to use different color for the proof. Okay, so let's let uh, so first this part of the proof. Okay, that's what the only if part, right? Only if, only if. That's clear. You know, if H is a subgroup, then obviously this is satisfied, right? Okay, so since H is a subgroup, uh, if A and B are elements of H, B inverse also is an element of H, and H has to be closed under this, the multiplication. So A, B inverse has to be also in H. So that's, pretty much clear. Right. So we just need to show the if part. So the other way around. In other words, the what is that? The H is a subgroup of G if this is satisfied, right? Okay, so that's if part. Right, so we suppose, that for any two elements A, B in H, A, B inverse is in H. Okay, so that's our assumption, and uh, under this assumption, we show that H is a subgroup, right? Okay. So first the thing I want to show is, the right. So in this case, let we have A, B, right? A, B, two elements uh, belong to, H, okay? Then, since A belongs to H, right? A belongs to H, uh, by this assumption, A inverse has to be also in H, right? Has to be in H by assumption. But then A, excuse me, A times A inverse is what? The identity. So we know that the identity element is in H. Okay, good. Next, now we know that the identity E is in H. So since E and A belong to H, uh, E A inverse, which is A inverse, right? But E A inverse has to be in H, so A inverse belongs to H also. So what did it show? We showed that the given H, right, its inverse element is also in H. Right. So we just need to show one more thing, right? Any two elements in H, A times B has to be in H. In other words, the subset H is closed under the inherited operation. So here AB are elements of H, right? And so, well, in the case, we also know that B inverse is in H. We proved it just now. So since A and B inverse belong to H, A, B inverse by assumption, right, which equals A times B, has to be also in H. So this completes the proof, right? This completes the proof. Okay, so here's another lemma. Suppose that G with this multiplication is a group, okay, and H is a finite, non-empty. There's another typo. Oh, this is shame, a lot of typos. Sorry about that. Uh, H is a finite, non-empty subset of G. And if H is closed under this multiplication, inherited operation, right, from this group G, then H is a subgroup. This is really, also, I mean, this is interesting because when H is a finite subgroup, I'm a finite subset, all you have to check is H is, the closed under the multiplication, then H is a subgroup. So even more simpler than previous criterion. All right, so let's prove this. Lemma, suppose that G with this operation is a group, is a group, and H is a finite subset of G. If H is closed under the same operation, right? Then H is a subgroup, right? That's the statement. So let us prove this. Since H is a finite subset, we can write H as set of the following elements: A1, A2, dot, 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 all the way to A sub n. Okay, right? Since it is a finite subset. Then for any, A in H, okay, for any A in H, so A times the subset H. So what is that? What does that mean? Actually, this is something we're gonna you're gonna see a lot later on. That this notation. We not only consider this, we are gonna also consider like H times A. So that's left coset, right coset. Later, like we are gonna call them left coset of H. By A, and also right coset H by A. Uh, but that's not important right now. What this means is, as you might have guessed already, that equals, A times A1, A times A2, A times A sub n. That's what it means. Okay, that's what it means. Okay, since H is closed under the multiplication, the operation of G, so this is obviously subset, subset of H. Okay, subset of H. On the other hand, if AI equals AJ, then, A is also, the member of group, so inverse element exists. Okay, we don't know whether A inverse belongs to H, but A inverse belongs to G, right? So, we can, multiply each side of this by A inverse. So, we get AI equals AJ. Okay? So, whenever these two are the same, AI has to be same as AJ. As you know, when there is a mathematical statement, its contrapositive is also true. So what's the they are logically equivalent, right? So what is like the contrapositive of this? The I can write it here, right? So this is equivalent to if AI and AJ are different, then AAI is not equal to AAJ. Okay, so that's contrapositive. These two are actually equivalent statement. So what does this mean? What it means is, this means that A times H has exactly the same number of elements as H. Okay, right? As H does. Right. So, the order of AH equals the order of H. And this implies that AH has to be same as H. Okay. Now, since A belongs to H, A belongs to H, right? A can be written as A belongs to H, but we also know that, maybe I should write that down. So A belongs to H, and we know that A equals A times H, So A equals A times AI for some I, between 1 and n, but I don't have to write that down. All right? Again, you know, so the one we saw earlier, like this is called the cancellation law, okay? Cancellation law. And we can do the same thing, So using cancellation law, what does that say? This implies A, I equals identity. In other words, we do have an identity element in H, right? Good. Now, since we know that identity element, okay, um, as in H, which is same as A, H, so, this identity element can be written as A times some AJ, okay, for some J. And so what does that mean? That means, remember like earlier, that we talked about like some basic uh, property, right? Basic properties of groups, right? So in this case, A times AJ equals E. So that's AJ has to be actually inverse, and inverse element exists uniquely, right? So anyway, so the AJ in this case, what this means is AJ is A inverse, and so we just showed that the inverse element of A is also in H. Okay. Now in our case, I picked A randomly, right? This is for any A in H. So we proved that, in fact, the finite set only requirement is H is closed under the inherited operation. And then we could show that the other required, the axioms are all satisfied. Okay, so the identity element belongs to H, and for any element A in H, A inverse also belongs to H. Therefore, Therefore, we just showed that H is a subgroup of G. So this completes the proof. Okay? All right, now, let us take a look at some examples of subgroups. So first example, the for any, the n, okay, so, the non-negative, no, non-negative integer, right? So zero or positive integers, n times, right? Z, that's, the set of all integers, right? Is a subgroup. Okay, you can easily check. It's a subgroup of the Z, the set of all integers with addition. All right. So here, n times C is again, like we defined before, and this is a collection of all numbers n times x, where x is an integer. In fact, these are the only, okay, these are all the subgroups of Z. Okay, so any subgroup of Z with addition takes this form, like a sum n times C. All right, and this is also part of a problem set. In fact, this is part of problem set 3 and number 3. Okay, and this is a hyperlink. So if you click on this, it'll take you there. A definition: the cyclic subgroup of G generated by an element in G, right? So that's what is that? A to the power K, right? Such that K is in Z. All right. So it is denoted by, this notation here. Okay. By the way, this can be positive or negative. All right. This can be positive or negative. So, there could be a positive, the subgroup, right? In that case, at some point, the K will terminate. Right? K will terminate. More examples. So let G be a group and A be an element of G. So here, C of A, okay, we are defining C of A to be a set of all G, like elements G, in the group G such that GA times AG. In other words, C of A is the set of all elements in G that commute with the element A. Then C of A is a subgroup of G. So C of A is called the centralizer of A in G. Okay, so the example, right? So, the A is an element of G, right? So C of A C of A is defined to be set of all elements in G such that G commutes with A. So GA equals A times G. Now let us show that C of A is a subgroup of G. Okay, so where there are different ways, you can show this, but let's 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 use the one of the lemmas we learned earlier, right? So let two elements G and H belong to C of A, the centralizer of A. Then GA equals AG, and also we know that HA equals AH. Okay, from here, HA equals AH means that, if you multiply H inverse, okay, I mean, G is a group, okay? H belongs to G. So, the H inverse exists. So if you multiply each side by H inverse from the left, right? So we have, what is that? A equals H inverse AH. And now we are going to do the following. I'm going to multiply this by H inverse from the right. So then we get AH inverse equals H inverse A. So what did we just show? We showed that, H inverse also, if H commutes with A, H inverse also commutes with A, right? Okay, we showed that. All right. Yeah, I think I just realized that the way I want to show is not necessarily simpler than like checking the identity belongs to C of A, and C of A is closed under the multiplication, and for any element in C of A, the inverse also belongs there, right? Yeah, that's not. So what I actually try to do, is the following. So in this case, I picked the two elements, right? So now let's do this. So I want you to show that actually GH inverse, right? GH inverse commutes with A. So that's by associative law. But now we just showed that H inverse A commutes, so that's same as G times AH inverse. And by associative law again, this is same as G A H inverse. And since G commutes with A, that's same as AG H inverse. And by associative law again, that's same as AGH inverse. So we just showed that GH inverse also commutes with A. So G H inverse belongs to C of A. Hence, C of A is a subgroup of G by the one of the lemmas, we talked about earlier. But like I said, in this case, we don't take much advantage of using the lemma because this is not necessarily uh, simpler. So actually, let's check that. So, an alternative proof, basically like we check everything, right? So, you know, but it's not hard. First of all, obviously identity element, the commutes with any element. So clearly E belongs to C of A because like I said before, that's the definition of E, right? I mean, part of the definition. So, the identity element, the commutes with any element. So, okay, now let G H inverse, oh no, sorry, what am I talking about? So pick any two element, right? Then G inverse also belongs to C of A. Okay, same proof. So here we proved in the earlier proof. Okay, that's exactly the same proof. So we don't have to do that. So all we have to do is now, the C of A is closed under the same operation. So G H of A times A, right? Now equals G by associative law, the same as G times H A. Now H commutes with A, so the same as AH, and by the associative law, that's G A times H. Now G commutes with A, that's same as uh, A times G H, right? And again, by associative law, this equals A times G H. Sorry for little silence. I had to take my morning medication. All right, so what did it show? We just showed that G times H also commutes with A, so that means G times H belongs to C of A. So C of A is closed. i.e. C of A is closed under the same operation, inherited operation uh, dot. So this completes the proof, okay? Right. So this part of proof, right? Although I coded the part there, like the showing that for any the element in the centralizer, right? Inverse element also belongs there, right? So even including that, this proof, right? This proof, right? Basically like checking each condition, right? For uh, C of A to be a subgroup, right, of G. This is not necessarily, right, uh, longer or more complicated. So, either way, this is okay. Second example, let G be a group and let Z of G, right? This is the set of all elements in G which commutes, with any element in G. And this is also a subgroup of G, and we call it the center of G, right? So this is again collection of the set of all elements in G that commute with everybody, okay, any element of G. Obviously, of course, if G is an abelian group, then center is the same as the group itself, right? Anyway, this is the part of the problem set number 3, I believe, about the subgroups. So I'll leave it as exercise. And third example, let G be a group and H be a subgroup of G. Then for any A in G, A inverse times H times A, that's this set, A inverse times little h times A, such that little h is an element of the subgroup. It's also a subgroup, okay? A inverse A inverse HA is also a subgroup. This is also left as uh, an exercise, right? And that is also part of the problem set number 3. Not difficult to show at all. Okay, let's move to next example, right? So, here's the symmetric group S3. Again, the symmetric group is what? The set of all permutations. In that case, S3 is the set of all permutations, all right, of the set 1, 2, 3. Okay, 1, 2, 3. So it is a group, right? As we talked about, and also its elements is what? 3 factorial, right? 3 factorial. Excuse me. So 3 factorial is what? 6. So we have 6 elements here. Okay, but you are looking at like something weird thing that you have never seen before. Yeah. So I said like these are permutations, but why like we are writing permutations like this? Okay, actually permutations can be also written as this cycle notations. So the one you are seeing are called cycles. Okay, cycles. So for instance, So we saw earlier like a 1, 2, 3, right? Belongs to S3. So what does this mean? This kind of thing is called, this is a cycle, okay? A cycle of length 3, okay? Cycle of length 3. So what it means is that, 1 goes to 2, and 2 goes to 3, and 3 goes to 1. Okay? So, in terms of like what the original notation, 1, 2, 3, 1 goes to 2. So 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay? So that's what it is, right? But also, we can write down this permutation simply using cycle notation. Okay, so that's cycle, that's a cycle of length 3. Okay, going back to my slides. All right, so this S3 has 5 subgroups. Subgroups. First, this trivial subgroup. Okay, uh, 1, 2, 3, 4, 5. When I say 5 subgroups, 5 proper, 5 proper subgroups. I should have said that. Okay, sorry about that. So proper subgroups, because S3 itself is also subgroup, right? So there are actually 6 subgroups, but among them there are 5 proper subgroups. Okay, so proper means that the subgroups that are not equal to S3. So this guy, and then here 1 and 1, 2. So this cycle here is what, length 2 cycle, right? And length 2 cycle, I'm going to talk about it in a moment, but uh, these cycles with length 2, they are called transpositions. Okay, transpositions. Here, A3, that's particularly important. Okay, so A3 is called alternating group of degree 3. So cycles of length 2, such as like 1, 2, 1, 3, or 2, 3, are called transpositions. I just mentioned, right? So any permutation, so this is important part. Any permutation can be written as a product of either an even number of transpositions, or in which case we call such a permutation even permutation, or an odd number of transpositions. Okay, so in which case the, it is called an odd permutation. And that there are exactly I'm going to talk about that. Okay, talk more about this in a moment. But the there are exactly the same number of even permutations and odd permutations. And I'm going to show you that the identity element is in fact an even, the permutation. Okay, so obviously, if you collect all the odd permutations, it's not going to be a group. However, if you collect all even permutations, okay, all even permutations. So here A3 is, as a matter of fact, 1, 1, 2, 3, 1, 3, 2. These are all even permutations of the set 1, 2, 3. Okay. Anyway, so so it is a subgroup. Okay, the set of all even permutations. That forms a subgroup of S sub n. Okay, the symmetric group S sub n. So, like I said earlier, there are exactly the same number of even permutations and other permutations. So, the order of a sub n is exactly n factorial over 2. Okay, because we know the order of S sub n is n factorial. Okay, so let's get to my notepad. So let's talk a little bit more about the cycle notations and transpositions. All right. So I mentioned earlier that the identity uh, permutation, right? The identity permutation. So here, one, one, two, three, one, two, three. That's an even permutation. Okay. So let's check the y. In fact, this guy can be written as 1, 2 times 2, 1 times 2, 3, 3, 2, and 3, 1 times 1, 3. Okay, so you can easily see that. Check that. What this means is, the one goes to 2, 2 goes to 1, so 1 goes to 1, right? And 2 goes to 1, 1 goes to 2, so 2 goes to 2. Okay? And so, we got this one. And here, 2 goes to 3, 3 goes to 2, so 2 goes to 2. And 3 goes to, 3 goes, yeah, so 2 goes to 2, right? Okay, 1 goes to 2, 2 goes to 1, so 1 goes to 1. Okay, and here, 2 goes to 3, 3 goes to 2, so, 2 goes to 2. And here 3 goes to 1, 1 goes to 3, so 3 goes to 3. So, this thing, that tells us that, the 1 goes to 1, 2 goes to 2, 3 goes to 3, right? So, it can be written as a product of these, the uh, transpositions, right? In fact, there are, it can be written as the product of the uneven number of transpositions. Actually, I just yeah, I just mentioned that, like, what, product of these two, right? Product of these two, product of these two, but that's not. I just wanted to show you, like, how that the product of two transpositions works, but that's not the way you do, right? Actually, this is product of all transpositions. So what I actually should have done is, let's uh, do it over again. Okay, right. So here 1 goes to 2, 2 goes to 1, right? So 1 goes to 1. Here, again, that you don't see 1. That means 1 is fixed, so 1 goes to 1. Okay? And here 1 goes to 3, and 3 goes to 1 goes to 3, 3 goes to 1. So again, like, 1 goes to 1, right? So 1 goes to 1. 2 goes to 1, 2 goes to 1, 1 goes to 2, so 2 goes to 2. 2 goes to 3, and 3 goes to 2, so again 2 goes to 2, and here 2 is fixed, so 2 goes to 2. Yeah, so that's how it works. Okay, in fact also the I mentioned that like any permutation can be written as a product of the transpositions, right? So for instance, like here, the cycle 1, 2, 3, okay, cycle 1, 2, 3 can be written as 1, 2, 1, 2, 1, 3, right? 1, 2, 1, 3, okay. So you can check it. So here 1 goes to 2, right? What about the right hand side? The 1 goes to 2, and so here 2 is fixed. The 2 goes to 2, so 1 goes to 2. 2 goes to 3, 2 goes to 3. Here 2 goes to 1, 1 goes to 3, so 2 goes to 3. 3 goes to 1, here 3 goes to 3, 3 goes to 1. So that 3 goes to 1. So these are the same thing, right? You can easily see. Okay, in group theory 4, we introduced the general linear group, okay, with this notation, right? So here, SL, GL of N, R, right? Here, R being the set of all real numbers. So here, we are going to introduce SL of N, R. That is a set of all elements in GL such that determinant of A equals 1. This is a subgroup of GL, and it is called the special linear group of degree n. Okay, so when you have it like a matrix groups, right? Matrix groups, the you hear the word like a special, it is likely what that means is the determinant of A. I mean the determinant equals 1. Okay, right. So let's check that. Okay, let's check that. I believe this is the last example. All right, so we are almost done. So SL of N R. That's A, set of all A in GL, general linear group, such that determinant of A equals 1. So you can easily show that like this is a subgroup of GL. How so? So let A, B, two matrices belong to SL. Okay? Then by definition, determinant of A equals determinant of B equals 1. Okay? In this case, determinant of B inverse also equals 1. What's the relationship between determinant of A and determinant of B inverse? By the way, B inverse is what? The general linear group is the set of all non-singular n by n matrices, right? Non-singular means determinant not equal to 0. So that means the inverse element exists, right? Okay. So determinant of B inverse is same as 1 over determinant of B. Okay? So in our case, this equals 1. I mean, you can easily show this, right? So this is actually well-known property, right? I'm gonna use different color. So determinant of A times B, that's a well-known property, right? Well-known property. That equals determinant of A times determinant of B. So using this property, uh, determinant of B inverse equals determinant of B and determinant of B inverse. On the other hand, B times B inverse is the identity matrix, so that equals determinant of I, which is 1, okay, which is 1. Hence, we get this property here, right? Okay, so anyway, so in that case, determinant, oh, that's too thick. So determinant of AB inverse, that's same as determinant of A times determinant of B inverse. So this is 1, this is 1, so you know this equals 1. So A, B inverse belongs to SL, right? So therefore, this guy is a subgroup of general linear group. The special linear group plays a very important role in many different subjects. Okay, not only of mathematics, right? Especially like the it is very important in something called the Lie group theory, representation theory, and the also in geometry, right? And also it plays the important roles in physics as well. So this is actually very important group. Okay. All right, folks. So this is it, and more details of my discussion here can be found in my lecture note at the following address. As usual, this is hyperlinked, so all you have to do is to click on this address, and it'll take you there. And also, in case if you want to visit my main Blogger site, you just click on this word, Blogger, which is hyperlinked. So it'll take you there. That's the place where you can also see lots of other lecture notes of mine in like a different subjects. Also, the group theory problem set 3 about the subgroups is available at the following address. Okay, that's pretty complicated, but it is hyperlinked. So you just need to click on this address, so it'll take you there also. Okay, the mathematics is the hands-on subject. A hands-on subject. What do I mean by that? You actually have to get your hands dirty. You have to solve problems. Listening to lecture is not enough at all, not nearly enough. Okay, there are things we can't teach you. There are things you can't learn. There are things you have to acquire by, you know, continued practice. I mean, it's just like the driving a car. You can't learn driving a car by watching, you know, the lectures. You actually have to sit behind the wheel. You have to do it by yourself, right? Same thing. So the mathematics in mathematics, there are lots of skills, like skills to prove, skills to solve problems, skills to you know compute. A lot of things, you just have to acquire them, and those things, a lot of them cannot be taught, cannot be learned. You just have to pick them up. How do you do that? By constantly, try to tackle, try to tackle problems. Okay, so doing problems are extremely, almost important when you study mathematics. The same thing goes for physics as well. Anyway, so this is it, and thank you very much for listening and watching my lecture. Bye bye.